am part of this webinar because I was the leader of Work Package 1 in the Just Win for All project. That was the work package for holistic assessment. We had a little bit of a different structure in our project. And then, okay, so this is what I wanted to show you today. So just a little bit of the complexity on how we have focused on that from our project. Some insights that we got, not only from our project, but from other work that we are doing in the group with other colleagues as well, and then some take-home messages. So basically, we based all our research in the idea that the energy system is complex and as such is unpredictable. You cannot reduce it, and it shows emergent behavior. However, we as modelers like to reduce it. We like to make models which are reductions of that system. We like to do forecast, which has a way of predictions, and we very hardly treat emergence. However, in sustainability science, we say that when you are dealing with a complex problem like this, we are talking about a weak problem. And that's a concept that is not new. In fact, it has many years and is coming from the field of marketing. A weak problem is one that shows 10 properties, they said, Rittel and Weber, and you can look at them, but the most important ones, the ones that I actually would like you to focus on, are that solutions are never right or wrong, but they are better than others or worse than others. And there is no immediate or ultimate test for a solution. So whatever that we do with our models, we don't know whether they are going to be right very often, no? And in that sense, then we have this idea of holistic assessment that in the end, it comes to deal with these holistic, with these weak problems. But what is a holistic assessment, I ask? I guess we both projects have to deal with this. And I guess the nice part is that everyone can deal with this in different ways, no? But what we can observe is actually when you look at the literature, and this is an examination of about 10,000 articles about wind power, what you find is that they are clustered. The knowledge is clustered. So what you see here is the correlation between different concepts and how they appear in different papers. And you see how the bluest is the more correlated, but it tends to be very much siloed within either natural sciences, engineering in the part of life cycle, on environmental engineering, or then design, no? Industrial engineering. So what do? We try to do include, or there are two ways of dealing with this integration. One of them is to put a lot of different parameters inside the energy model, and that will give us the best solution. Or another way, another frequent way, and this is very reductionistic, but it's kind of two poles of one thing, would be that we try to create models for each one of the parameters and then connect them. And then again, we try to find the best solution. However, our proposal was, how about we don't try to include and find only one best solution, but just try to have a space of solutions that is beyond the optimal, no? Beyond the techno-economic optimal. So the proposal that we did in Just Win for All is to have the energy model doing what an energy model do, which is techno-economic optimization, and then assessing social and environmental issues with semantics and models that can actually understand social and environmental issues. So this is just a very, very summarized way of our how we do our work. So basically, we do deal with the life cycle of the wind turbine in this case, and then we insert it in the context of the rest of the energy system, and we calculate the environmental impacts and the social impacts and how these impacts can be actually managed by the societies, because in the end, we are doing this because we want energy, right? So the tool is called WIMBY. I just leave it here for your reference. And if you have any questions, we can answer more about it. So basically, the proposal is that we model the energy system, and then we try to integrate different social and environmental issues and have a desirable, maybe, option space. No? To check that, we also assess preferences. So holistic assessment is not only about many environmental parameters for us, it's also about the preferences of the people and maybe even geopolitical issues. So here are some insights that we got, and I think justify why the type of assessment done in WIMBY is also necessary, right? So the first thing is that input data matters. If you happen to be doing a life cycle assessment with EcoInvent for wind turbines, here I show you a work that Michael Sierra did, where he's showing how either you underestimate or overestimate impacts if you are using EcoInvent as compared with a parametric model he developed called WindTrace. Here you have the reference for the paper. Another insight that we got is that it is okay to mix different impacts, and we don't need to reduce them all to either money or any other common unit. But we can actually just provide this option space. Here you have in the left 900 configurations for the energy system in Europe, and in the right, the different impacts that are coming to each one of these 900 configurations. So as you can see, for example, the configurations with more winds, that will be wind onshore, or these ones here, which are more wind onshore and offshore, hold lower impacts for lower values for key impacts that like mineral depletion. Another thing is that when you do a holistic assessment in this way, you get to compare against the optimal, the techno-economic optimal. So here I'm showing a work developed by Alex de Tomas, and you can see how the option space move not only to reduce but also to increase. So as the future is uncertain, as we are moving to this weak problem space, what we might want to know is what is actually the margin that we have to move up and down of that optimum. So here you see how, for example, land use gets reduced in the option space. But for example, materials clearly are increased because of the amount of infrastructure that we need to build. Again, the paper is here. We also studied how these impacts correlate with the security and the variability of the impact. So here you have a comparison between the impacts or the normalized impact according to the optimum and the Gini index, and see how there is a clear relation between the complexity or the variability of the system and the impact. So the more resilient our system is in terms of energy, the more impacting as well. This is something we need to consider. When you do it this way, you can also regionalize the impacts. Here is a comparison between the business as usual proposed in the Spanish NECP and the scenario for 2024. So what will be the change in impacts when they are regionalized in the future? You see how some regions are better than others. And because our project was called Just Wind for All, we were assessing justice issues. The regionalization of the impacts was also very different, something that both projects share, the regionalization. Impacts are not only happening on site, they are also happening abroad. And here, very summarized, I just leave you an idea of the dimension of the impacts that we are displacing when we are importing energy technologies. So if we want to fight climate change, so this is our purpose, then maybe considering impacts in other places is important as well. So not only local impacts. So just very, very quickly, wow, this is very, okay. The holistic modeling, as we covered it in Just Wind for All, must consider both social and ecological issues, but also the relations between them. We propose to explore new workflows, and for that we need information like the one the guys are going to present in a bit, which is very useful also for us. Maybe just to keep the idea that there is no unique solution, that solutions are many, and that we need to find a way to understand this space of solutions and how to choose between them. And just an idea of the projects that funded our research beyond just Wind for All. And if you have any questions, I'm happy to answer them. I don't see you, Dominique, and I don't hear anything right now. So
no, because I think no one said something. Thank you for the presentation. As we are a bit restrained in time things, I would now just directly head over to the next presenter, or the first presenter of the webinar, which is Peter, and give the floors to him. If there are questions for Christina, please feel free to drop them in the chat, and maybe you have some time to revisit them later. Thank you.
Welcome also from my side to this webinar. So I'm Peter Berger from the Paul Scherrer Institute in Switzerland, and I will talk about health impacts of wind power, and in particular health impacts due to accidents. And this means that we are now outside the space of normal operation for the next 15 minutes. And then I guess for the rest of the webinar, we are coming back to normal operation. So impacts also of accidents, of course, they can be diverse. We have human health risks, we have environmental impacts, financial losses, and also perception as a subjective factor here. I will in this presentation only talk about human health risks, and in particular impacts from accidents that can lead to fatalities, injuries, or also disamenities. Let me just make a little spoiler, since this is a high-level webinar, and come with some of the key findings before we go into the technical details. So wind accidents in Europe are generally rare events and manageable. So that's not untypical for accidents. Large countries, also in terms of existing capacities, they lead in safety across Europe. Safety improves with experience and operational scale. We can also see that for wind power in our data. This is something that is also very well known for other technologies. And even if you're speaking now just about wind, and you may see some absolute numbers, you should always keep in mind that if we make a comparison, wind remains far safer than fossil fuels. For now, what I would like to cover in this presentation is a few slides about the research methodology, then the regional safety performance across Europe, because WIMBY was also trying to downscale impacts. Many models do NOx 2 or even below. Then a few words about which factors are driving health impacts, and then also put wind a bit into the larger context to put some substance on the statement I just made on the slide before, and then close with a couple of conclusions and recommendations. So the methodological framework basically can be put into 4 phases or key steps. So we first, within the project, compiled a database of wind power accidents. So there is a similar approach like for life cycle assessment. So we take a full chain approach. So that's not just the turbine that's operating, but we also look at maintenance. We look at construction. We look at end of life here. The database is all or mostly open access data. It's open access data, but for verification purposes, we also used some additional commercial databases and industry data. We also linked the accident data to wind farm data and to other GIS layer. And then the core is basically a statistical modeling, because accident data per se are rare events, so you don't have a lot of data. And at the same time, it's also very much differing across countries. So we are using what is called a hierarchical Bayesian model. And that's a relatively complex thing, but you can then with few data still generate robust results. We express the health impacts in a unit that is called disability adjusted life years, something that's pretty common in life cycle assessment, not that common for accidents. So I think it was also nice to do that for a first time for the accidents. And then we downscale to the NOx 2 level and of course we also make this comparative analysis. We consider the time frame from 2023. 24 data are now available, but a bit too late for this project. And basically, these three parts I will show you in the rest of the presentation. So let's start with disability adjusted life years, or DALYs. So one DALY, that's basically 1 year of lost healthy life that you would lose due to an accident. And then there are three components that we have modeled. So it's the so-called years of life lost. So that's the total number of years lost to premature death. So that would mean if an accident leads to a fatality. So then you can also be injured. So that would be the years lived with disability, or there can also just be some more psychological impacts due to an accident. That's then the years with anxiety disorder that we have at the end. This all is then also coupled to global databases, the global burden database. So these are large activities of World Health Organizations and others that allow us specifically per year and country to calculate the weights that we should apply to individual accidents. We then can calculate the total DALY per accident, and we can downscale that further on and also map it in a geographic information system. The actual Bayesian hierarchical model, I don't want to show you any equations here, but basically it has 4 levels. So you go from the global level to the individual observation. So you have a nested structure, and this nested structure helps that the model can also do information sharing or borrowing from countries with more accidents to countries that have only a few data points. And of course, this is not just linearly done, but you have to tell the model how this should happen. Then to have a robust estimation, there are several mathematical tweaks that you have to do. So you have to choose in a Bayesian model always a prior. So that's basically the info without the data that you have, your expectation how the data should behave. Then we have implemented 2 different prediction models, and in the end the model generates a lot of output files that we then can use to analyze the data. But yeah, if you are interested in that, there is a forthcoming journal article also that will go into more details here. Then for the end of my presentation, I would like to show a couple of results. So first, the regional safety performance. So what you see here, these are just the top 10 performing countries in Europe. You see the blue squaring for each country. So basically that's the mean. And then you have the range when you downscale it also to the NOTS 2 units. So we can basically distinguish 3 groups here. So the first group shows an excellent performance in both dimensions. So that's Germany, United Kingdom, France, and Denmark. So when we also compare that against the data and the descriptions we have for the accidents, we see that these are also countries who have comprehensive safety management practices. Then we have a couple of countries with mixed performance. So on one of the 2 aspects here, they are not performing that well, while on the other one, normally they are quite well still. And then we have a couple of countries that have challenges in both directions, and that can also be an indication that there would be some more systemic safety issues. But I have also to make a disclaimer now. Now we just looked at the top 10 countries, and of course, if we would have add all these 39 countries in Europe that we analyzed, then we have to put that a bit more into relative terms. And even if we would scale to the global scale, because then we see that even if we can differentiate within Europe, Europe as a whole is still performing much better than more less developed countries, of course. Then if we downscale that, and here you see a map of Europe at the NOTS 2 level, so that's below the 2 hierarchical levels below the country level, then we also see that there are some regional differences. So Western European countries, they predominantly show lower health impacts. Central Eastern European countries, particularly in the Balkans, you have higher impacts. And then in Southern Europe, we can also see that there are differences among countries. So some have relatively uniform impacts across the whole countries, and others show more regional variation. And then two general points at the end. What is also important is we have regional heterogeneity. So we see local factors influence risks, and you see also these white areas. So basically there we have data gaps. For the time being, when there was no installed capacity, we haven't calculated risk indicators. In principle, our model also allows to make predictions for such areas. We will implement that in a second stage. But of course, you will then increase the uncertainty that you have in the modeling for these areas, because there is no data, and that of course weakens it. But it's possible. Driving factors. So of course, what makes a country safer? It's also for winds, what we found for other energy technologies, it's experience and scale. So that means operational experience, how much you deploy. Maintenance is a very important issue. And then also governance. So what regulatory frameworks are in place? And we are not speaking of the European level here, but also what is at the national or even subnational level. Standards and very important, not just that you have these things, but that you also have processes to enforce that. And then, of course, if you want to learn, you also need a comprehensive reporting of incidents to know what are the lessons learned. Last but not least, let's put wind onshore into context. So you see on this slide fossil technologies, hydropower, nuclear, and a couple of new renewables. Overall, we can say that the fatality rates, here we're looking now at fatality rates and not at DALIs, because we haven't modeled the DALIs for all the other technologies. We see that wind is about 1.2 to 1.5 orders of magnitude better than fossil technologies. Renewables generally have low fatality risk, and wind is somewhere in the middle of the pack. And factors that affect the profile of risk for wind, of course, is working at heights. So we are 50 stories tall, something like that. Also construction maintenance, that's an environment that's a bit risky always. We have rotating machineries, and of course, what is also worthwhile to note is the majority of fatalities that we observed are attributable to workers. So for the accidents, it's much less the general public that is affected. And if I sum up, it's of course sounds always trivial, but we should learn from the leaders, adopt their best practices. But of course, that's sometimes not that easy, especially if it's about countries, because who wants to say that others are better? I think we still should strengthen some of the regulations if we compare it to other energy technologies, although we are on a very good path here. Invest in training, that's also something very trivial, but it's not always done to the extent possible. And of course, to fill the data gaps, we should also enhance reporting, make sure that it's publicly available, because if people cannot get the data, then they will look it up in the internet, whatever they can find, and that's probably not the data that are best suited to inform objective decisions. And with that, I close, and thank you for your attention.
Thank you, Peter. Thanks very much for the informative talk. That was very nice to see. As we are a bit short in time, maybe we can have one short question for Peter. Just unmute yourself and speak if you have a question. Okay, and if there are no questions for now, please use the chat box.
I have one quick, if no one else has an answer. Peter, I wanted to know, you said regional factors matter. Could you somehow link the weather with occurrence of accidents? Like if we're in a country where the weather is often pretty bad, does that increase risks of accidents, or is it completely unrelated and more due to other factors, other regional factors?
No, it's a factor that matters. We also looked into that. I didn't show it today, but of course, when you have storms or other harsh weather, that can have an impact. But at the same time, I mean, you're not just running your wind farm during a storm. I mean, there are also automatic mechanisms when you shut them in.
Okay, thanks.
Okay, thank you. For all other questions, I would like to point to the chat box. Please post your questions if you have any, and Peter will catch up on them. And with that, I'd like to introduce the next speaker, which is Roman Sacchi, and he will continue now with impacts on noise.
Yes. Right. So yes, my name is Roman Sacchi, not Sacchi, as I could have heard it. And I'm going to be talking about human health impact related to noise propagation from wind turbines. So in the context of the WIMBY project, we developed a model to, or a tool to model noise propagation from wind turbines and its effect on human health. Noise is increasingly being considered by different authorities, national, European level, and worldwide level. And often the noise emitted by wind turbines is overlooked, or at least it's not a priority topic when talking about wind turbines. But it is not nevertheless important to study it and try to understand better the effect it can have on human health. So of course, wind energy is a low carbon form of producing power. But if you're nearby, if you're living nearby an operating wind turbine, you can be affected by it in different ways. It can go from being simply annoying all the way to preventing you from having a good sleep. Not having good sleeping conditions can, of course, lead to more serious problems like cardiovascular issues, diabetes, but it can also have... Yeah?
I think we cannot see your screen. So
I haven't shared it? Okay.
No.
I thought I did. No, sorry about that.
No problem. Thank you.
Yes, but also besides health effects, not having good sleeping conditions, for example, can have tangible effects on your daily life, your productivity, etc. For this reason, the World Health Organizations recommend exposure limits. So we have basically two numbers. During the we have this so-called LDEN. So this is time-weighted exposure to noise in decibel, taking into account the exposure during day, evening, and night. And it is recommended to be below 55 decibels. And the L night, meaning that the exposure to noise strictly at night, should be below 40 decibel. So with that in mind, that was the context to create a tool that could tell us for a specific wind turbine with specific attributes such as power, heights, location, and so on, to have this tool to tell us how would the noise of that wind turbine propagate geographically and also hourly over the year. And once we are able to define that, then we can convert these noise emissions to LDEN and L night, which is defined by for which we have formulas, notably from the World Health Organization, and then further convert that once we know who lives in the area to DALIs, which is the concept that Peter has been explaining to you, to assess how people are affected by this noise exposure. So I'm not going to go too much into details, but the model, once given location and the height of the wind turbine and a few other specifications, is able to calculate the propagation of a noise emission through space, and then it will add attenuation terms, which are a physical effect that will come to attenuate, to reduce the propagation of this noise. So we will add, for example, the geometrical dispersion effect, the effect that the atmosphere is able to absorb part of this noise emission, the effect that describe the fact that the ground is also able to absorb part of this emission, and also the fact that we might have some natural barriers like hills and forest and this kind of or changes in topography that can attenuate these noise emissions. The mathematics behind that is described in this ISO standard, so we are merely following the standard here. And then we are able to calculate these LDEN and L-night indicators, because we know how much noise and the way the noise propagates for this particular wind turbine hour by hour over the year, because we are fetching wind speed time series. So we know on average how much the wind is blowing at this particular location. What we're doing, once we've established how much noise is emitted and up to which extent, we add any sources of existing noise prior to the installation of the wind turbine. So that can be noises from nearby highways, industrial areas, airports, railways, etc. So you have an illustration here where we have a few wind farm clusters in Maribo in Denmark. And so our model has calculated the noise propagation. So this is a contour map. So for example, the green circle is 30 decibels up to 70 decibels in purple. But of course, we withdraw these areas where there was actually already a source of noise emission, and this is the case with the highway E47 passing through the wind turbine here. So this is actually showing how much the increase in decibel on top of the existing noise emissions. Then, having this information, we're able to connect that to some of the models from the World Health Organization, which has been providing some relation functions between exposure to LDEN and L-night to DALIs. So we have some curves here for different sources of noises. Unfortunately, and this is the main limitation of this work, we don't have such a curve for wind turbines, because, as I told you at the beginning of this presentation, the noise from wind turbines is often overlooked. When looking at the different noise profiles of these different noise sources, we ended up using the profile of road traffic, which seemed to be the one that is the closest to the profile of noise emitted by a wind turbine. And by profile, I mean how the sound distributes over the 8 octaves of the sound spectrum. And so we see with an increasing in LDEN values, we have an increase in DALIs, although the relation is not necessarily linear. And these curves are for DALIs caused by high annoyance, when you're simply annoyed by the noise. And these curves are for high sleep disturbance, but we have curves for other types of disease. Now, connecting these two, we've done a small simulation. We took the case of Switzerland, and we simulated the electricity production of a 2.5 megawatt wind turbine in many places in Switzerland, except on lakes, to get the overall production over the lifetime, which we assume to be 20 years. And then we overlaid a population map on that, and we simulated the propagation of noise of each of these wind turbines. And the map that you're seeing here, let me get a better pointer, is essentially the absolute increase in DALYs due to the installation and operation of the wind turbine, of that 2.5 megawatt wind turbine, going from green, which depict an increase in DALYs from 0 to 1, so 1 disability adjusted life year, all the way to red, which means above 40. And of course, the closer to populated areas these wind turbines are, the higher the DALYs. But also what we saw by simulating these impacts with wind turbines of different sizes is that while you do have more DALYs with an increase in the power of the wind turbine producing more, you get a decrease in DALYs per kilowatt hour produced. So what is driving these DALYs? So if we look, this is the same map, but if we look at what is making up these DALYs, actually we see that most of it is caused by high sleep disorder, so preventing good night sleeps. But at the same time, heart disease and diabetes also contribute, although to a much lower extent. But of course, this needs to be put in perspective. So what we did is we calculated the overall DALYs of that wind turbine over its entire life cycle. So we use life cycle assessment, and we used a method that allows us to calculate the DALYs per kilowatt hour for that wind turbine, considering all of the types of impacts besides noise emissions, such as impacts on human health via climate change, via the release of carcinogenic and non-carcinogenic substances. And so what we see when we take the median of the DALYs caused by noise, it remains minor compared to the DALYs caused by the use and release of toxic substance during the life cycle of the wind turbine, which is notably during its manufacture. So that was the first finding. And the second finding was that if we add the DALYs caused by noise to the life cycle results of that wind turbine, and we compare it to other means of producing electricity, we see that adding the noise, which is this little red segment that we put on top of that 1 to 3 megawatt onshore wind turbine, doesn't change its ranking DALY-wise compared to other electricity production technologies, where we get much higher scores for technologies such as lignite and oil and some hydro and some hard coal-based power. So overall, the impact, even when we consider noise during the use phase, remain much lower than fossil-based technologies. Yes, that's it. And those interested in using the tools, it's available for download from GitHub. Thank you.
Thank you, Roman, for the insights. That was another highlight, I think, of the WIMBY project. Is there a short question for Roman? Yes, Dick, please go ahead.
Oh, yes, it's a comment really on, you mentioned a level of 55 dB, which I agree with you, that's what World Health Organization says generally. But there is quite a bit of work showing that for wind turbines, the appropriate level might be nearer 45 dB. And the WHO 2018 report, whose name I can't remember now, but it's the European Region report, actually sets a a preliminary level of 45 dB for wind turbines. So it is recognized that the levels need to be lower in wind turbines.
Yeah, so we looked a bit in the literature, and the relation people have to wind turbines is not always rational. So you might wonder why people, because at the end of the day, sound is sound. So why people are less tolerant to wind turbine than other sources of sound, and there might be other reasons for that. And some of those reasons could be if people, for example, like we saw that in Denmark, where people by law can have an economic stake in the nearby wind turbines, are much more tolerant to noise than if they don't have any economic stake to it. And people will tend to be more tolerant with noise, higher noise coming from an airport than lower noise coming from a wind turbine. So it is true, and we've seen that. And from a modeling perspective, we can just reduce the threshold. We just choose to follow the WHO recommendations. We could follow others, but it really begs the question whether those are really grounded in science, or just how people perceive wind turbines, because maybe they are initially annoyed by them because they don't have any stake in them, and therefore, even though they produce less noise, they will be perceived as more annoying. That's something that maybe is deemed more useful for society, like an airport or a highway. But yeah, I agree with you. But I think it's not straightforward. It's pretty hard to elucidate people's opinion like in a clear way with respect to wind turbine. I have that feeling.
Yeah, I think you're absolutely right that a lot of it is non-acoustic factors. I mean, this happens with noise all the time, that people are affected by non-acoustic factors.
Yeah.
Okay. Thank you. I would encourage you to use the Q&A session. Actually, there is already a question for you, Roman, so maybe you can address that throughout the webinar. And with that, we head over to our next presenter, Xing Shuang, who will show us now her shadow flicker model. Xing Shuang, the stage is yours.
Yes, can you see my screen?
It's loading.
Okay.
Yes, now we can, but not in presentation mode yet. Okay, now we have.
And now? Yeah, okay, perfect. Hi, everyone. So I'm Xingxuan Chen from Wucheng University, and I'm going to introduce the shadow flicker model that I developed. And what is shadow flicker impact caused by wind turbines? This is the intermittent effect caused when the rotating of the blade of the wind turbine casts shadow because of the sun on the other side. So imagine the wind turbine here is just like rotating, but then the shadow here will also be flickering. If you are living in this house, then that can be a noise. So why this matters? Because the annoyance caused by the shadow flicker can affect people, and particularly in rural area, and then if you are closer to the turbines, because it has less buildings or artificial stuff surrounding in the surroundings, and then if you are closer, then the shadow also casting you in like longer period of time. And this can, like the discussion of Roman and Dick before, this can also be like rise the annoyance because you have the combination of different factors. Like if you have noise and shadow flicker at the same time from the wind turbine, then people can feel more annoyed, or people are perceived risk already in general in their environment, or there are some people have individual sensitivities. Then this all in combination can trigger or enhance the annoyance of the shadow flicker. And this annoyance can then generate stress, sometimes even lead to health issues. But there's again also no direct health effect, like leading to disease and so on. But then there are a lot of there are some research focusing on the annoyance caused by shadow flicker. And also, there are multiple countries have regulations or suggested guidelines that about the tolerance levels of shadow flicker, which is usually, well, in Europe is usually 30 hours per year. And so that's why we need to assess shadow flicker impact, and then we need a good tool, bestly open tool to do it. But when I just started this project, like a bit more than 2 years ago, there's no there's no open source tool that are tailored for shadow flicker, which also includes topography impact. So yeah, most of the researchers or in industry, they use either commercial softwares like WinPro, or sometimes they develop surveys and then for the local community, and then build a statistic model for the local predictions. But these are like limited because this is really differ by case. So then our goal is to build an open source handy shadow flicker tool. So this is the the flow diagram of the tool that we developed in the end. To be short, we need the digital surface model, so basically the topography information, and then we also need the wind speed data. And there are three main steps. First one, we calculate the time steps density, and then we calculate a single time step shadow flicker impact, and we aggregate it to the full time span. And in the end, we have the shadow flicker impact in hours per year. So this is how we calculate how we include the topography impact in our tool, which I wouldn't go into details, but these are from the topography data, and then you can calculate one time step shadow flicker impact is located here. And then we also have to calculate the shape of the turbine casting on the topography, which is shown here, and then after having one time step, then we can aggregate it to the full year like this, and this is in the mountainous area in Spain. So you can see that the lighter area here means like higher elevation. So basically a hill here is not so the shadow cannot go through it, so it makes sense. And then next we can aggregate all these time steps because one time steps means certain period of time of coverage, and then we can aggregate this into a frequency map shows in hours per year already. And then next, we also consider the view shade impact, because imagine if you are in this hilly area, then you won't be influenced by the shadow flicker impact anymore. So we just exclude this area by using the view shade tool here, and then we have this final shadow flicker map. Okay. So the next, we can also calculate it for multi-turbine, and then, for example, for a wind park. And we also reclassified the shadow flicker impact with below 30 hours per year and more than 30 hours per year, which the dark blue, the dark purple one is more than 30 hours per year, which means you have more shadow flicker impact if you are closer to the wind turbines. Okay, and this is how it is shown in our interactive map, which I believe in the end, Luis will introduce more about this. And then there's also validation part we did, that we compare it with the standard commercial software WinPro across 98 sites in Spain and in the Netherlands, which represent the flat and the mountainous and the flat terrain. And also we only focus on the above 30 hours per year area, and and the results are quite well. It shows a strong agreement with the accuracy, which with the Pearson's correlation coefficient with quite high level, and then also the difference between the areas are below 10%. So it is quite well performed, and then also showed more enhanced terrain sensitivity here. Actually, you can see we have sometimes more detailed of terrain sensitivity because we use like 20 by 20 DSM than the WinPro. I think I'm muted. Okay, so there are still some future work that needed to be improved. First, it is quite simplified. Basically, we want what we showed here is like worst case scenario, which the turbine is always facing to the sun. So it casts the largest area of the shadow. And then also we haven't include the cloudness and then the humidity data, which can improve the real situation simulation. And there's also a limit of the input data that you need. So, okay, I hope you can hear me. To conclude, we have a very well performed open source tool that can, well, is validated for at least the European area. And then it is now on the WIMBY Interactive Map. And the next one would be how to balance the wind energy target and the social environmental impact, which I think this will be the whole topic of today. But then that can also lead to other collaborations that I want to invite people here. If you want to use the tool, then you can find it here. It's fully open sources, and then also some methodology are listed in this conference paper. But if you've thought about some collaboration opportunities in the future, then yeah, just come to me. And then that's it.
Thank you, Xingsheng, for the presentation. We have room for some questions, so please unmute yourself and go ahead to ask questions if there are any. Okay, not for the moment. There was one for a request for your paper, Xingsheng. Maybe you can share that, or the deliverable. If there are more questions throughout or afterwards, please use the Q&A button. And with that, I will open the floor for our next speaker, Ricky, which will present his work on scenicness. Ricky, the floor is yours.
All right, thank you. I hope you can hear me. Yeah, and I'm sharing my screen as well. Okay, good. Yeah, so good morning, everyone. I'm Ray Hong, a PhD student at the Chair of Energy System Analysis here at ETH. And today I'll present the GIS-based landscape scenicness prediction with machine learning for Europe. So first, a short introduction. So we all know from other speakers as well that wind projects usually face high social opposition compared to other renewables like solar. And actually, visual impact of wind turbines is usually one of the most biggest reason for social opposition, and which is also one of the main driver for to make wind projects the target of many social campaigns, such as like local unwanted land uses, not in my backyard NIMBY, which is inspire our name for the project, or even banana build absolutely nothing anywhere near anyone. So this is crazy. And existing study has already tried to address this visual impact of wind turbines through first one, visibility, or somehow consider the exclusion of scenic areas while during the planning phase or through resource assessment. However, these studies are usually focused on a national scale. And for the WIMBY project, we're trying to develop this continental scale analysis. So the goal will be to make a continental scenicness map. However, we have a lack of scenicness data for the EU. And also there are studies trying to use deep learning to get the scenicness rating out of photographs. However, we also don't have photographs that covers every location within Europe. So here we propose a method to predict landscape scenicness using OpenGIS data and machine learning. So here is an overview of our method. Remember, our goal is to train a model to predict the target value on unseen data based on the reproducible features. So first we have the target data, Y, which we have a scenicness data from the Great Britain, and we categorize them into different scenic classes. And then we have the feature data, which is the X. You use X to predict the Y. And using the feature data, we use some calculation, and then we have these calculated indicators, and we have some features that we directly use the raw data to fit into the model. And these are the two features that we use, and both the target and the feature we fed into the machine learning model to train our classifier. And after training, obviously we need to evaluate the performances of the model. And yeah, after picking the best performing one, we feed in all these reproducible features across other EU countries, and then we get a European scenicness map. Yeah, so simple. And then for now, I'll give you a short introduction of the scenicness data that we use. First is, so we got this scenic or not data set, which is crowdsourced ratings of randomly presented pictures, and ask users to rate them from 1 to 10. And this covers the whole Great Britain with approximately 1 square kilometer spatial resolution. And as you can see here, I put a picture of the spatial data set. As expected, Scotland, Wales, and the Lake District are the most scenic places in the UK. And to use this data, we assume that the ratings that we get are the consensus on scenicness rather than place attachment. So what is place attachment? It means that when someone grows up or live at a certain place, it has some emotional ties to a certain location, hence the rating will tend to go high. So to use this data, we need to use some pre-processing to reduce the noise. And we also focus the training on the non-urban areas because we don't put wind turbines in the urban setting. So we get the mean ratings and categorize them into either binary or ternary classes using different cutoff thresholds. And then we train the model with these different targets that's using different thresholds to select the best performing model with the best cutoff threshold. And next we'll talk about the features. First, 4 are the calculated features. So basically we use for wilderness indicators that's based on the landscape study here in Switzerland. First one is naturalness, which is basically a rating of the land cover and the altitude of how natural that land cover is. And then ruggedness is basically the standard deviation of elevation within a specified window. So how fast the terrain changes. And then the remoteness. So we calculated across the whole Europe, the shortest time for any location to walk there from the nearest road. And also last one is the human impact. Basically, that's the sum of the number of human infrastructure within each pixel. And here we consider 10 different infrastructures. So we have calculated these 4 indicators for UK and also for Europe. And as I mentioned, we also have other raw features directly from input data. And here's the complete table of all of the features that we feed into the model to train. And so the selection of these features, it was based on literature review and also data availability that covers approximately the whole Europe. And so our focus scope based on the data is EU countries. It's EU 25. It's basically the whole EU by excluding Malta and Cyprus, but plus 4 additional countries. That's Norway, Switzerland, Liechtenstein, and the UK. And this data, it has mostly has very high spatial resolution, but we need to resample all the data to approximately 1 kilometer by 1 kilometer to match the scenic or not data set. Yes, and then next I will give you some small details of the model training. If you don't know machine learning that well, these are just some words you might want to know, but no need to go into details. So we use spatial stratified split, make sure the data was sampled from different locations and the same distribution. And we use open sampling techniques and also adjust the sample weight. And also the chosen algorithm was gradient boosting. And yeah, we use some cross-validation to tune the hyperparameters. But these are the details. You don't need to care much about it. Then we have some conclusion from the model training is that actually we discovered that the model can only better distinguish the differences between highly rated locations, meaning, for example, a location rated 7 and 8, the model can categorize them with a higher accuracy. But for locations that's rated from 4 to 6, unfortunately, the accuracy was somehow low. And we can extract the feature performance from the trained model. And we discovered that land cover and also the rated naturalness of land of the land uses are the main drivers that contribute to a scenic class. Yes, so enough of the training. Then we go to the final predictions. So here is the final output of the machine learning model. We make predictions across the whole Europe. That's either binary 0 and 1 or ternary 0, 1, and 2. So it's highly scenic, others, or highly scenic, scenic, and then the rest. And yeah, according to the results, we rated around 17 to 24% as highly scenic, exceptional scenicness value across Europe, and around 14.3%, as you can see here, in the ternary model. That's in the intermediate class. And you can see there's a cluster of highly scenic areas. That's Northern and Southern Europe, and the Alps, also Northern Scotland, and these are mostly the coastal and mountainous regions. And there's also, we overlay this map on top of a resource assessment model, and there is a considerable amount of highly scenic area land that's eligible for wind deployment. So as you can, around 40% of the highly scenic areas are actually suitable for wind projects, and this highlights the land competition. And as for validation of our prediction, so we use the existing wind turbine data set that we have in the WIMBY project, and we found that around 80% of the existing wind turbines are actually located in these black areas, which is the other scenic ratings. Yes, so these are the results. So here we come to limitation, the outlook. So the main limitation of our method is, yes, the lack of training data from other countries. Basically, we're training the model on Great Britain and predict the whole scenicness across Europe based on the British opinion, you can say it. And then there's also potential bias in the scenic or not data set. It was rated on pictures. There could be biases on the photographer's techniques and also the unknown directions of the photos that was presented. And we also can have limited domain knowledge, meaning that the tank features that we selected might not fully capture the relationship. And there could be errors in the raw data, could be magnified during the processing. And here's finally an outlook. So obviously, to improve the accuracy, we need to crowdsource more scenicness data from other countries to improve the representativeness of the land coverage. And then the application of this scenicness data, we can combine it with visibility analysis to have a comprehensive visual impact assessment. And we can also possibly assess the visual impacts of not only the wind turbines, but also the associated infrastructure, like the grid extension towers, etc. And yeah, that's the end of my presentation. These are my references, and thank you for your attention.
Thank you very much, Ricky, for the nice presentation and to present such a complex topic in in time. We have time for questions, so please again unmute yourself and directly go ahead to pose your questions to Ricky. Maybe if there are no questions, and as we have a bit of time, you said one of the limitations is to improve the picture, the level of scenicness you want to assess actually depends on the angle of the photographer. Do you have, or would you have, what would you choose as an alternative if not using these pictures? Do you have, is there an alternative to that?
Yes, exactly. Yeah, another direction could be use open source satellite images. However, this, as we all know, covering land cover is already derived, basically, the land cover from the satellite images. So there could be like a potential correlation between the features that you fit in if you already use the land cover. But yes, it is another topic that potentially you can use, like building a neural network, trying to, for each location, you get a satellite image, and train the model based on that.
Okay. Thank you. I still don't see another question. So maybe just a very basic question. What was the main challenging part of developing your model?
Good question. Yeah, I think the main challenging part is actually all the features. So we need to select a set of features that could, based on literature review, of course, that has potential relationship to the landscape scenic ratings. And as we all know that scenicness rating is a subjective rating, to have like objective indicators to capture the subjective rating in itself is kind of challenging already. And having the features that cover enough data to cover all the locations that we want to explore in the project, it is challenging to just collect all of this data and somehow come up with a data set or feature space that does not have very high collinearity. Yeah, I would say that's the biggest challenge, but we do what we have to do with so far.
Yeah. Thank you, Ricky. Thanks for the
Right, thank you.
presentation. Again, if you have more questions for Ricky, please feel free to use chat box and Q&A session. And now I will continue with the presentation about the life cycle assessment, which we conducted here at WUB. And we is me, basically. So I'm Dominic Huber, a researcher at the Free University of Brussels, and we have conducted a life cycle assessment of wind turbines, which I'm going to present today. So instead of just bringing another slide on increased global mean temperature, which I think by now all aware of, I wanted to look into something else and start the presentation. And I've chosen hot extremes in this content. And I brought as a starting point different visualization of our globe. So we can see here in this map the different regions all over the globe, and we can see actually in red that we have experienced an increase in this extreme or hot extremes almost in all areas. And the second observation is that these little points in every shape is actually indicating a high confidence in our human contribution. So one step to limit hopefully such extreme events could be the deployment of renewable energies such as wind turbines, and this is what we are talking about today. And I will now continue with a proper assessment, or one of the many assessments that we did, and we have heard this term throughout the presentation a couple of times, but I think we have not heard sound or the definition of the methodology. So I will start with this. So what is actually life cycle assessment about? So it's an international method on environmental assessment. It considers an entire life cycle, such as presented here on the right side. So it goes from raw material extraction over production and assembly to the use stage, and then recycling and final disposal. And then the objective, or it is also characterized by providing a systematic overview with the objective to avoid shifting of environmental burdens from one category to another. Then the characteristics of these methods are that it's a relative approach. So we try to express environmental impacts relative to the function of the system that is provided. And it's normally an iterative approach, meaning that we start with the data collection, then we run a first round of results, and we see, okay, actually this was not what we were thinking about or what we expected, and it's not as precise. So we need to go back and collect a bit more data, refine them, change them. So now that you have an understanding of what life cycle assessment is, I want to show you what we actually did. So we have already seen a couple of times or heard the term life cycle assessment. So this again includes resources extraction, the component manufacturing, and then, no, shit, I'm sorry. I just wanted to use the presenter. It's fine. Then installation, operation, and end-of-life treatment. And this is what we call system boundaries. And then once we define this, we can actually calculate our impacts. And then these impacts, in our case here, are normalized to a functional unit to compare it. And that's, in our case, electricity produced over the lifetime. So what did we actually do? We used an existing life cycle assessment model, which was developed by Roman Satki, that is also has presented earlier, and we have added here the location of a certain wind turbine, or the possibility to add a location of a wind turbine. And then we read out various information. And so one objective to read or include information was on the ISO code in order to sample more regional data sets. But then we also wanted to identify very simply the type of installation, so whether it's on or offshore. We wanted to have more information or size the foundation type according to the sea depth at a given installation offshore. Then we wanted to improve the calculation of the cable length to connect the wind turbines then to the electricity grid. And we wanted to increase or refine the transportation distances from component manufacturing to the installation. And then in the end, the electricity yield, so the annual electricity production we obtain from the WIMBY map. So now I will focus within this presentation on three main parts of the presentation or of our refinements. And the first one is on the foundation of the offshore wind turbines. So in the default or in the original model, there was a monopile foundation modeled, which can cover roughly up to 30 meters of sea depth. And this is bottom fixed, as we can see here in the picture. Then what we did is we added floating turbines, so they can cover then sea depth between 30 and 60 meters. And this could be then, for example, a semi-submersible floater. And then beyond 60 meters, a spar buoy could be installed to cover also this depth. So as a decision criteria, we read out of a multimetric map the sea depth, and then at the given location, we determined which type of foundation should be included. Then in terms of lifecycle inventories, we used inventory data from a study published by Garcia and Terrell in 2022, which represent data from pilot studies on a spar floater with 9.5 megawatt and a semi-submersible floater of 6 megawatt. And then the tension leg, so this part here, or the platform, we scaled based on the rotor power, and the cable length we sized based on the sea depth. So this was one refinement that we made, and another one was related to the electricity connection of the wind turbines to the national electricity mix. And that was actually quite challenging because these data are by nature sensitive data, so it's very hard to get specific locations of this because it's sensitive data. And here on the right side, we can see an open access repository that try to remodel the European high voltage grid. And in this data repository, they also added some more data on the grid infrastructure, for example, such as electricity buses. And these one we used as a simplification as a connection point to the local grid. So what we then actually did is we calculated the geodesic distance between the turbine location and the closest power bus in the European system. So obviously this is not a technically valid solution. So it's just an approximation because we, for example, ignore the voltage level. If you have a very big farm, maybe you could enter at different voltage levels. That would mean then another location, for example, versus when you have a smaller turbine. Then also topology, we have heard enough about this today, but we also didn't take into account like lakes and infrastructure such as airport areas and so on. So it's literally just a direct distance connection between the buses and the location. Then in terms of transportation distances, we have consulted 2 large European manufacturers, and we checked then where the different locations for different components are. And then we just simply looked them up and identified them on Google Maps, read out their coordination, and then we calculated again the distance of this turbine to of the components manufacturing to the turbine location. And then how we selected the transportation distances, we simply assumed that when the turbine is closer to one location, that could be a selection criteria. And now let's look into some results. So I have demonstrated then my model with 2 case studies. So one is for onshore and offshore, which we can see here on the right side on the x-axis of this chart. And then we look into climate change impact per kilowatt hour produced. What we can see here now is results for on and offshore turbine. And we can see that the parts here in the lower, they represent the components that were refined with more detailed inventories. And we can see that the contribution is actually quite small. Then the main impacts, they actually steer from the main components. So these are still the big towers and the rotor and the nacelle and so on. So then we also can see that due to higher electricity production, the offshore results here quite better than the onshore. And when we compare this to standard eco-invent data sets, we also can see that the model resulted in some improvements. So then we didn't only look into one turbine, but we also looked into fleets. And here I brought the example of Belgium. So what we can see here is, again, climate change impact on the x-axis and the number of turbines that perform in a certain cluster of impacts. And we can see in white here the current onshore, in dark gray the current offshore, and in this light gray future offshore installation in Belgium. So when we look at the averages, we can see that we have an average of 2, 5, and 8 gram CO2 equivalents per kilowatt hour for the future offshore, the current offshore, and the current onshore fleet. And then maybe to just put this Belgian fleet a bit into other numbers, so we can see in terms of materials that there's actually quite a lot of material bound in this fleet, which highlights a bit the last stage, so end-of-life treatment. And so when we look what materials are actually used in the Belgian fleet, we can see that it would be enough to rebuild 150 times, for example, the Eiffel Tower using all the metals. And then for the components materials, we could reproduce 560 Airbuses, 800 A320. And we can also produce a lot of plastic bottles for this. So this was a very rough and fast overview. We also looked into, for example, biodiversity losses due to land use changes, but I'm not going to detail this. There's also more analysis on drivers of the fleet in the deliverable. And I have also published this as part of my thesis chapter. And we are currently working on submitting this as a journal publication, both the biodiversity losses and the LCA model. So with that, I would like to thank you for your attention. And if there are any questions, I am happy to answer. Yes, Samuel. Please go ahead. Can you unmute?
Hi, Dominic.
Yes.
Yes. Hi.
Allô? Oui? Je t'entends
Yes,
de nouveau, oui.
Okay, now Philip is talking.
Yes. Maybe let's use first Samuel and then Philip, we go with you.
Okay. Thanks, Dominic, for the very interesting and nice presentation. Sounds really impressive and a very nice tool that you have developed. I have a quick question. Do you also consider the vessel emissions, especially for offshore wind turbines that, burn fuel to do the installation and operational maintenance, etc.? I ask because we've seen in our studies, and that it's also in agreement with other papers, that those impacts account for about 1/3 of the carbon footprint of offshore wind. And if that's missing, it just might be maybe interesting to add to have the full picture in the future.
Yes, the maintenance is currently focused on onshore, so this doesn't include what you just mentioned. So we neglected this, yes.
Okay,
But yeah, it's a very fair point, and I know that there's actually quite a lot of impacts coming from this. So yeah, I fully agree. Actually, we're trying now to, or looking into refining a bit the maintenance stage. But yeah, how and when we will update this is not yet defined.
Okay, thanks.
Thank you. Philippe, you also had a question, or did you unmute yourself by accident? Yeah, maybe not. Good. If there is no more question, because I don't see any more, then we can move on with the last model presentation, which will be presented by our Monica. And with that, I give the floor to you.
Hello, thank you, Dominic. Can you see my screen?
Yes, perfect. And we can hear you.
Perfect. Okay, so today I'm going to talk about financial compensation and participation schemes in the wind energy sector from a regulatory view. And I would like to start with the question why financial participation and compensation schemes, hence money that is paid to municipalities and or residents in the vicinity of a wind park, why is this important? First of all, there's a fierce competition in the wind energy sector after the introduction of auction systems, which reduces citizen participation. Then the best spots or conflict-free spots are already taken, so it's getting more and more difficult to find nice locations. Taxes are not always paid locally, but at the headquarters of the wind park or at the national level. So municipalities and residents might feel like they don't get anything from the cake. Other benefits such as CO2 reduction, job creation, and economic growth are not considered. They seem to be too abstract as to be considered by the locals. Then we have EU measures to accelerate the energy transition after the update of the Renewable Energy Directive. And now member states actually have to define renewable acceleration areas by February 2026, which is also increasing the pressure on states to create a successful wind energy transition in their country, meaning that they need good acceptance rates. So this actually then leads to the result that many member states have, especially in the past couple of years, introduced many regulations and policy documents on financial compensation and participation schemes. We can see a particular rise after the Repower EU plan has been announced, which, like I just mentioned, says that member states have to accelerate the energy transition. So in my analysis, I have analyzed legal documents of the EU 27+3. I could identify 44 documents in 19 regions and 21 in 19 countries and 21 regions that ask wind park developers to compensate municipalities and residents with monetary payments. And what I've then done is to differentiate between 4 types of financial participation schemes. The most prominent scheme are fixed compensation payments. An example is in Austria, in Burgenland, where wind park developers have to pay 3,000 euros per megawatt installed and year and transfer the money to the municipality. And I could identify 32 of such schemes in Europe already put into regulation. The second scheme I identified is debt-based participation. Here's an example from Germany, NRW, where wind park developers must offer residents the opportunity to invest in the project through subordinated loans, and they will then get interest rates out of it. So per megawatt, 90,000 euros of investment opportunities must be offered to residents. Here I could identify 4 schemes. Then we have profit-based participation. Here's an example from Slovenia, where wind park developers have to share 3% of the annual revenue with the municipality. And then we have equity-based participation. Here's an example from Spain, the Balearic Islands, where at least 20% of the project's ownership must be offered to municipalities. And here I have identified 9 schemes. And then I have also identified 10 schemes that allow developers to choose any of these 4 schemes just defined. What I've also done is to then look into these fixed participation schemes and compare which country has the highest payments and where, in other words, where developers have to pay the most money to municipalities and residents. I have used an example wind park with 25 megawatt for my calculations, and it is represented in annual payments. So the dark blue countries mean that for a 25 megawatt wind park, a municipality receives more than 150,000 euros per year. And the lighter the countries, the less the compensation is. So countries are Norway, France, and Finland are the top runners, but also Denmark, which is not really surprising, actually. What I've also analyzed was the binding force of the schemes. Because I could see that regulations sometimes use a very soft wording. So I could identify 3 different levels of binding force. The highest binding force I have defined as must be offered, and there they use the keywords are shall or must. So in Burgenland, it, for example, says the wind power levies shall accrue to the municipality, and the holder of the permit is obliged to pay the levy. Then some regulations have only used soft words such as may or can, and other countries have defined no standards at all. So I have considered these 3 levels of binding force in my next analysis, where I wanted to know how many of the identified fixed payment schemes are really hard law and really must be implemented by the countries. And with respect to fixed payments, it's still 27 schemes. And this is also the most prominent scheme still. Then debt-based scheme, there is no legal binding scheme, actually. With respect to profits-based schemes, I could identify 3 schemes, among others in Denmark and Slovenia. Equity-based, I could identify 2 schemes. Then what I've also done is I've done a little justice analysis to identify, is there schemes that are more just than others or are perceived by residents more just than others? Because that, of course, is important to increase acceptance levels. So I differentiated between distributive justice, what is being distributed, recognitional justice, who benefits, and procedural justice, how is the distribution process of the money governed. And based on this analysis, I have come up with several design recommendations for these schemes. And on the level of distributive justice, I would recommend wind park developers to initiate with the compensation payments already during the construction phase and not only after. Because also, so I've connected this with the literature review, and their citizens have said that actually the highest amount of disturbance is already during the construction phase, of course. So they would like to receive compensation payments from that moment on. Then the payments should be extended until site restorations. Only a few schemes prolong payments until the site is restored. Some countries, for example, say that payments should only go for 7 years. Others say it should be for 20 years. But this would ensure that the environment is already, again, put in a good condition. Then payments should be linked to the actual impact. For example, some schemes say that only the hosting municipality should receive payments, but tension may arise to neighboring municipalities that don't get any compensation, even though they're affected as well. And only a few, schemes should plan ahead and discuss repowering. Only a few schemes mention repowering, so it's not really clear whether financial compensation payments are also paid after the wind park is being repowered and how these schemes will look like. So this should also be considered. On the level of recognitional justice, it is important to define the eligibility criteria based on effectiveness. Again, ignoring the neighboring municipality might lead to tension. Then one should include residents affected by earlier projects. Austria, for example, has included a retroactive effect of its law, meaning that it doesn't only address new wind parks, but also those that have already existed for 10 years. This is kind of rare because so Austria is one of the few countries that has extended the eligibility because there's always the fear of introducing a law that affects the past, because companies must trust the law and how they're doing business, but there's solutions to that. So Austria has offered a nice solution. And participation should also be facilitated for low-income households. If you think of offering project shares to residents, low-income households might not be able to afford them, but also there's mechanisms how to involve them. And on the level of procedural justice, it should be a misuse of third parties should be avoided. In Denmark, for example, wind energy shares were offered to residents and the municipality, but then it was actually companies who bought most of the shares. So also there's possibilities to avoid this. Then transparent reporting should be mandated. If money is transferred to a municipality, the municipality should be obliged to also show how the money is spent locally, so to make sure that it really reaches the citizens. I've heard this one anecdote of somebody working at Wind Europe who said that the Greek mayor at the Greek Ministry of Environment was disappointed after they introduced such a law, because apparently it was, did somebody say something? Apparently the mayors just kept the money for themselves and citizens didn't see it in the end. And yeah, this is similar to the other one. It should be ensured that funds are used in the citizens' interests, for example, by earmarked spending or through the setup of citizen councils who decide how the money received should be spent. Yes, and then I've just brought a few examples that I found very interesting. For example, Brandenburg in Germany has introduced an official website where citizens can see how much money the different municipalities receive. Another example of the Netherlands shows how laws that support co-ownership in wind and solar energy development are implemented into regional laws, and the darker, the better the implementation has been. And in Scotland, you can find a map where you can click on different projects, and it shows you a general overview over the project, but then also how much community benefits go, how much money goes to the municipality, and whether there are opportunities for shared ownership. So thinking in a bigger picture, it might be interesting to extend or to create such a map for the whole of Europe, where countries can also inspire each other and show what is possible to create with the funds received. And then a last short example, because I don't have so much time left, unfortunately, is how to finance co-ownership. So I would like to just quickly mention, how residents can afford shares, especially low-income households, when there is a wind park. And actually, Lovich, my boss, suggests that a fiduciary could be set up that takes up a loan in the name of the residents and gives the residents part of the loan to then afford the project shares, and the cost of the loan is then repaid with the dividends paid out to the residents. So this would be an example that I mentioned earlier, how to also include low-income households in co-ownership schemes. And this example I will just skip for now. And yeah, thank you for your attention.
Thank you, Monica, for this overview. That was very, very interesting. And I would suspect that there are questions. I already see the Q&A box popping up, but maybe someone wants to directly go ahead and pose a question to Monica.
I think it's maybe not a question, but just a comment, because I see that what you presented there also right now in practical use in the UK where people actually not really trust that you pay into a fund for the municipality. So this transparency is really a thing which needs to be further worked on. Because when people don't really trust you that there's money available for them, however, it doesn't really help them to pay into such funds, right? So we have actually exactly that situation, to make that more transparent and helpful for the people.
Okay, thank you for your remark. Jan Frederick, if you want, you can also share your email, then I would be interested in that if you have a link to that or anything.
Yeah, definitely. I can do that.
Thanks.
Or will do that. Yeah.
Good, thank you. I think now we have had a lot of input, so I would suggest that we move on to more practical things and give the floor to Luis for demonstrating how these models now are represented in the WIMBY maps.
Thank you, Dominic. I actually have the privilege of presenting the work of all these people together. It's just a lot of data models that have been presented today. I think the only thing that we haven't included here is the final developments of Romansaki with the DALI about the noise, and obviously the work of Christina, which I hope someday in the future we'll be able to include also in the WIMBY map. But otherwise, everyone is covered here. So to give you just a small jump in, this is for the colleague that is speaking German. Could you please close your microphone? Thank you. So the first message for everyone is this: what you are seeing in your screen at the moment is also available online. Yeah. All right. You can find it on their map.wimby.eu. It's pretty available. It's still the beta version, but basically all the functionality that you saw today is already there. And I'm going to make a short intro of some general capability of the map. So this map, you will see that it looks a little bit like the new European Wind Atlas for a reason, because it also includes the data from the European Wind Atlas in terms of wind speeds and wind resources availability. One of these layers that I like is, for instance, the power density one. It shows you in watt per square meters where you can get the most energy in basically in the continent. You have it for 100 meters or 200 meters. Very related to what we saw before. Well, we have multiple things, but we have, for instance, also the accidents map of Peter Burger, presented in here with the units in DALIs, and all the numbers that you saw before are also reflected here for the entire continent. We also have the landscape scenicness for the United Kingdom, for the place that is best validated, as you saw from the presentation of Ricky. Sorry, Ricky, I know you as Ricky, and you will stay Ricky for the long term. And you can also go and check other capabilities, for instance, the necessary install capacity that you will have if you will want to become net zero by 2050, but this was not presented today. So I will skip the details on this one and go to the, well, probably the most attractive thing that you will find in this map, something that you definitely cannot find anywhere else. And for that, I will just zoom in into a country that I find very beautiful, but also very particular. I'm going to zoom in into Slovenia. I'm going to check the wind resources and assume that I'm looking for a place to put a wind farm. Maybe let's go. I see some high power density over here. Why Slovenia is so interesting is because the install capacity is relatively low. So with the example that I'm going to make now, I'm basically going to multiply the install capacity of Slovenia by 2. And for that, I just have, you probably saw that there is a new button that got activated, that this is a Start a Wind Farm simulation. But we also have some exclusion zones that we know because of ecology. So if there is a natural protected area, you will see a green surface. If there is residential areas or commercial areas, you will see these purple zones. If there is some infrastructure, you will see here the train lines or the highways. And if there is some sort of physical constraint, because for instance the slope of the mountain is too high, you will also see this orange hard constraints. So, well, I will find a place to put our wind farm, and then I can just click in this button. And for now, you can select an area of up to 10 square kilometers. This is 7.57, which is good. I just made a square, but it can have any shape you want. I will try to accommodate 5 turbines in here. And you can select between different types of technologies: onshore low winds, offshore 10 megawatts, and offshore 15 megawatts. Also to see which is the difference depending on the size of the turbines. You let it run. And while I'm talking, the tool is calculating or is looking for the places with the highest energy production and the lowest wake. This is an optimization model that has been optimized to being quick. So you really get these results as soon as possible. And then you get your 5 wind turbines. And then based on these locations, you get a lot of more information on the first side. You get the annual energy output, you get an estimation of the capacity factor for the places where we also Monica gathered data on regulations for the continents, and for the countries where we have a lot of data, this section of setbacks distances is very, very long. Slovenia was unfortunately not a WIMBY country, so the information that you get here is relatively limited. But you get the median of all the distances across the continent that you will find in relation to residential buildings, distances to motorways, to railways, and all sorts of infrastructure. And you will also see these numbers reflected if you go and click on the soft constraints. And then you will see who, based on regulation, actually only one of these 5 wind turbines that will be optimal could be located at the moment. But more to discuss on that maybe later, so I will deactivate the soft constraints again. And I'm going to go to the impacts that we were calculating. So while I was talking, we got also an online calculation of the noise impact that Romain presented earlier today. So you get also different levels of noise for each one of the turbines in the wind farm, and also a coverage of each one of them. So the highest level is 60 decibels, and it goes until 30 decibels. So I think the thresholds that we were discussing were 55 and 45. So 45 is probably going to be somewhere in between the orange one and the yellow one. The other calculation that we performed in the meantime was the shadow flicker estimation. That's the model from Sichuan that we developed at Utrecht University. You can see the hours with more, the places with more than 30 hours of exposure in this darker violet, and then in a softer violet, the places where there is shadow flicker, but less, way less time during the year. We also have some models that were not presented today. It is, for instance, the land use and land cover change to estimate the actual shape of the wind farm, and also tells you which kind of land use will be changed to be able to construct it. We have an estimation of the levelized cost of electricity. We have a high-level estimation of the created jobs in jobs years for these 5 turbines in this particular country. We have some data on collision risk for birds and bats. That is also one of the results of the other work packages. And also that we saw today is the information about local benefits that in Slovenia will be fixed payments and revenue-based participation for this particular turbine. If you click on it, you will get a larger explanation, and you get also a link to go for the place where this information was found. The models about the LCA and the biodiversity impacts related to land use change that were presented today by Dominic, they are basically there. We were just waiting for changing one of the underlying databases so we can make them available. But in general, these two are going to be also 2 boxes like the ones you are seeing here. The nice thing is you can go and save your project with the button here and basically share it and distribute it to anyone you would like to discuss about it. In general, we are looking, well, for future collaboration in a way to sustain the tool. I can happily comment to everyone that we already got some resources to start working on a game out of this tool to make it easier for education purposes. But otherwise, I left 6 minutes to questions because I think everyone can just go and play. But I will prefer to use the chance in case anyone has any questions about the map.
Thanks for the demonstration, Luis. There is one question in the chat box already, and this is on the availability of the different individual layers, whether they are available for download outside the web application.
Yes, they are going to be in the latest. I haven't made the proper statistic, but I will say 70% is already available in a page that is called Yoda. That is basically the Zenodo from Utrecht University. You will find the layers in there already, most of them. And the ones that are not ready there, they are going to be for sure available in by December this year. But we are working on it. I'm trying to consolidate the list, but they are going to be available on Yoda. And we are bringing up a publication out where you will find a summary of all the models that are included in the map, and also the links to every single one of the data sets. We don't have a download function directly in the map, but all the data sets that were presented there are available, as well as the models that you saw. They are all open source. So, well, you can basically just go and follow up on the individual repositories. I don't know who made the question.
Thank you. Yes, I think that answered the question very well.
Mhm.
There is another question. Please also just unmute yourself, then I don't need to read out. But in the meantime, Christina asked, how can we access the maps until you that you presented now, Luis?
You just have to go to map.wimby.eu. I would like to put that in the chat. But I don't have to put it in the chat, otherwise I cannot put it, but I can put it here in the Q&A maybe.
I will post it.
Yeah.
Thank
Is
you,
now
Luis.
there as a question? Yes, thank you, Christina. Again, beta version, we're trying to make a decision if keeping this beta version running for a little longer or the final version, but in general, what you see here is almost the final version of what is available. This has been thoroughly tested. We are still doing some feedback rounds, but don't expect big changes apart from some additions of additional models like the LCA one and the biodiversity one. Okay, no more questions. Okay, Samuel Kynes, please go ahead.
Hi, yeah, Samuel from Technical University of Munich. Thanks, very impressive tool, really cool. One quick question, is here the objective optimization energy production? And are there also other objectives available, for example, minimizing carbon footprint or costs? Or is that
Unfortunately not. Unfortunately not. We have been discussing this. Well, there were simply not resources allocated to that. So once again, we are looking for basically money to continue. We are also, I mean, if there are other contributors that would like to support further development, we're also open to discuss options. But we don't have it. In the paper that we're bringing out, there is literally 2 sentences about that the kind of thing that we would like to do. But yeah, it's not there yet.
So for now, wake interactions are minimized, right? In the optimization.
Yes, for now, what you have is the maximization of the availability of resources and the minimization of the wake internally for the farm. So we don't take into consideration nearby farms. But that's also on the make. I hope we get resources to do it. But yeah, I mean, this is a complete product that has a lot of chances to continue growing. Let's see what happens in terms of resources to do so.
But already this version is really, really impressive. Thanks for the presentation.
Thank you.
Luis, there's another question from Christina Drahici. She asked, what is your vision with regard to a mapping future for offshore wind?
If I understand the question properly, the WIMBY map also works offshore. Only not in this level of detail. There are many things that we don't have. For instance, think of the birds and bats data. We don't have that kind of data for the offshore. And we are just trying to get resources to extend the WIMBY map to offshore. But so far, well, I don't have any confirmation of anything. So you can go and basically draw a polygon in the sea, and you will get the same algorithm running. But for some of the models, you simply will not get an answer at the moment because there is no that kind of data in the background. But yeah, if you have some resources, happy to talk. We will be happy to extend this. I don't know from which kind of institution you are joining, but we are also looking for some sort of partnerships with the industry. I mean, keeping this alive is relatively cheap if you think of the kind of revenues that a large company might have. But for academics, well, we live on a project by project basis. So yeah, if you have any hints on resources or partnerships for us, please come back to me. We will be happy to also further develop concrete things for needs, let's say, for offshore development.
Okay. So I think we finally saw a lot of things, and we also saw it very applied. Thank you for the live demonstration, Luis, and thanks again for all the presenters of today. I hope it was informative. I would also like to thank Marta from Deep Blue, which helped me to organize this. And with that, we will close the webinar. I think it's an open invitation. If you have any remarks, requests, then feel free to get in contact. You have our details. Just send us an email. There was one final remark from Marta.
No, guys, sorry. I just wanted to send an emoji to say that you were very great. Sorry, I reached the end by mistake. Yes, sorry.
Good. Then thank you very much.